In this video we're going to look at a type of model called analysis of covariance, and we're going to fit that in the framework of linear models. So the data we're going to look at concerns mole rats, and let's draw a graph of the data so I can explain what the variables are. So the response variable here is the natural log of daily energy expenditure, and then we have two predictor variables. We have a quantitative predictor variable, which is the log body mass, and then we also have a categorical predictor variable, which is called cast, and it is distinguishing lazy mole rats, so layabout mole rats, and or infrequent workers, and we also have frequent worker mole rats, and we're trying to figure out whether the relationship between daily energy expenditure and body mass differs according to the type of mole rat, whether they're lazy or whether they're frequent workers. So we're going to start off by fitting a no interaction model. So if we're fitting a no interaction model, then we just put a plus sign in between the two predictor variables here, and then we can visualize that model fit like this. And so just as in the last video when we talked about no interaction models and interaction models, we had a no interaction model where the lines representing the effects of one of the treatment variables, the two lines that were on the graph were parallel, and so that's the same case here. And so this dashed line here represents the relationship between log daily energy expenditure and log body mass for the workers, the frequent workers, so the open circles, and then this solid line represents the linear relationship between log daily energy expenditure and log body mass for the layabout mole rats, the lazy ones, the filled in circles. Okay, we're going to also fit an interaction model. So remember, the way to fit an interaction model is to put a multiplication symbol in here. So we do that, and then we can visualize that model fit. And so when I run this code here, what you should be expecting is the scatter plot will stay the same, but these two regression lines that we have will be allowed to not be parallel, so they'll probably shift a little bit. So sure enough, there they go. And so usual statistical question in this context is what is the improvement in fit when we go from the no interaction model to an interaction model? So when we did this in the last video, we had a very dramatic change from the no interaction model to the interaction model. Not only did the lines become non-parallel, but one was going up and one was going down. So that was a big change. That wasn't surprising that we had a significant improvement in fit there. But here the change is a lot more subtle. Here's the no interaction model, here's the interaction model. Not a whole lot of difference. So I don't think we're going to see as dramatic a result in this case as we did before. But let's see. Let's go through it. So we're going to do an f-test of the improvement in fit, and so we're going to lay out our 4 steps as usual. So first step is to state the null and the alternative hypotheses. So the null hypothesis is that there's no interaction between cast and body mass, and the alternative hypothesis is that there is an interaction between cast and body mass. The second step is what is the test statistic. So if we run this ANOVA function, we get a test statistic here, so 1.0188. And then the third step is to state the p-value. So there's the p-value, 0.3206. And then the fourth step, make a decision, draw a conclusion. So we're not able to reject the null hypothesis here because the p-value, 0.3206, is not less than the significance level, 0.05. So we cannot reject the null hypothesis that there is no interaction between cast and body mass. So what we were speculating about in our graph was that there didn't appear to be a big difference going from one model to the other, and sure enough, this f-test is telling us that this model is sufficient. The no interaction model is sufficient. We don't need an interaction term. Okay, so what happens if it turns out that the data are telling you that this model is sufficient? So what we want to do now is to test the main effects. So we want to test whether there's an effect from log body mass on log daily energy expenditure, and we want to test whether there's a difference in the two casts of mole rat, the lazy ones and the worker ones. So to do that, we have to do something a little bit complicated. We have to work with something called the type 3 ANOVA table. Because if I was to just do this, and just use the regular ANOVA function, I get what's known as a type 1 ANOVA table. And a type 1 ANOVA table doesn't do quite what we want it to, because a type 1 ANOVA table, also known as sequential, is fitting the terms in order. So first of all, it fits a model with log mass, and then it fits a model with log mass and cast. If there was a third predictor here, the third step would be it would fit a model with the first predictor and the second predictor and the third predictor, and so on. So it's building up the model sequentially, and so each f statistic and corresponding p-value is looking at the effect of each predictor given that the predictors that come earlier in the sequence have already been fit to the model. And so that's not quite what we want to do here. What we want to do is to find out whether there is a linear relationship between log daily energy expenditure and log body mass when we fix the other predictor, when the other predictor is already accounted for. And then similarly, we want to do a test of whether there's a linear relationship between log daily energy expenditure and cast when we fix the log body mass. And to do that, we need to calculate what's called a type 3 ANOVA table. So to do that, the way to do this is to fit another model, which I'm going to call no interact model type 3. It's the same formulation as before for this part, but then we add another argument to do with the contrasts. And so we've just got to add this bit of syntax to the model to get the type 3 ANOVA table, to fit the type 3 ANOVA model first, and then we can get the table. And to get the table, we have to run this function, and this function has a crucial capital A at the beginning. Here's the regular ANOVA function. And you see it's spelled with a lowercase a. But if I type ANOVA with a capital A, this is coming from a different package. It's the car package. So right at the beginning here, I had to make sure I loaded the car package. And you can read all about it here, but you can see we can do different types. We can do type 2 and type 3, whereas the regular ANOVA with a lowercase a does type 1. So, but we want to do type 3, so that's why I've got type 3 here. Okay, so if we run this, then we do get what we want. So now we can do an f-test for improvement in fit from adding log mass to a model that already has cast in it, and we can do an f-test for the improvement in fit for adding cast to a model that already has log mass in it. And in this case we can see that the p-values are both less than 0.05, so we would reject the null hypothesis in favor of the alternative hypothesis and determine that there is a linear relationship between log mass and log energy when we account for cast, and there is a linear relationship between cast and log energy when we account for log mass. Okay, that brings us to the final part of the video where we can make some predictions. So we're making predictions for this no interaction model, and for the sake of argument, let's predict the values for a log mass of 4.6. Okay, so what we should be getting is a predicted log daily energy expenditure of around 4 for lazy mole rats, and if we go up to here for the workers, we'll get about, what is that, 4.4 for the workers. Okay, let's see what we get. So we can do the calculation by hand. So if I get the summary of the no interaction model, so these are my parameter estimates, and I can use those to get a prediction for the lazy workers. So again, we have to think about what is the reference level here. The reference level is whatever's left out. So the reference level must be the lazy mole rats, the layabouts. So if we want a prediction for the lazy ones, we're going to take our intercept, minus 0.09687, and then plus 0.89282 times 4.6. So that comes to a shade over 4, and that matched up with what we had on our scatter plot over here. And then for the workers, the working mole rats, we're going to have intercept minus 0.09687 plus the slope times log mass, so plus 0.89282 times 4.6, and then we also need to add on the 0.39334 for because this represents the difference between workers and lazy mole rats. So we do that calculation and we get a shade over 4.4. So again, that matches up with what we got on the graph. And then if we don't want to do those hand calculations, we can just use this code to get the predictions calculated for us. Okay, I haven't really mentioned checking assumptions in this last series of videos, but really we ought to be checking assumptions each time we fit a model before we start using it to make predictions. So just as a quick example, we could look at a residual scatter plot. So this is for this no interaction model, and what we would like this plot to look at is just like a random scatter of points with a roughly symmetric cloud of points above and below the horizontal line at 0, little noticeable curvature as we move from left to right along the horizontal axis, and approximately equal variance of points above and below the horizontal line at all predicted values or fitted values. And that's the case here. You might be a little bit concerned about these 2 points down here. Like, it'd be nice if those 2 points just weren't there, but they are, and so we have to just live with that. But it's just 2 points. It's not worth getting too excited about just 2 points when we have a sample of 35 points here. So I wouldn't be too worried about these 2 points down here. It's possible that these 2 points might be outliers, and so maybe we should investigate a little bit further. And that is probably what I would do at this point. But I'm not too concerned. I'm not going to throw the whole model out just because of these 2 points. I might spend a little bit of time looking into these 2 points, but at this point I'm not going to throw the whole model out just because of that. And then we can also check normality with a normal quantile plot, QQ plot, and that's pretty good. The points are pretty much along that line, so everything is good from the normality point of view. Okay, so that is how to fit a analysis of covariance, or ANCOVA, to the linear model framework that we've been looking at in the last series of videos.